Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review what you need to know about probability. So this semester is all about continuous random variables. X is a random variable if the value it takes differs due to chance. Same definition as last semester, but this time we're looking at continuous random variables. That means the random variable X can take any value within a range. Now, when you have a random variable that's continuous, the probability it takes on a specific value is 0, because there are always infinitely many possibilities for the values the random variable can take. Instead of finding the probability X takes a specific value, we find the probability X takes a range of values. So the way we find the probability X is within a range is we integrate this special function Px called the PDF or probability density functions. So if a function is a PDF, it must satisfy these two conditions. Firstly, the PDF can only take 0 or positive values for X between A and B. That's what this one says here. Now, A and B are the values that the random variable can take. For example, if the random variable is between 5 and 10, then the PDF must take only positive values between 5 and 10. The second condition the PDF must satisfy is the integral over all possible values that the random variable can take must give you 1. The area under the curve between A and B must be 1, where A and B are the lowest and highest values that the random variable can take. So let's now look at a related function called the CDF. So the CDF, or cumulative density function, it calculates the probability X is up to and including a certain value. So this is the relationship between the CDF and the PDF. The CDF is the integral from A to X of the PDF. Here, A is the lowest value the random variable can take. Another way to say that is if you differentiate the CDF, you get the PDF. So let's look at an example. So the uniform distribution is probably the simplest continuous distribution. So here X is between two values A and B, and the PDF is just 1 over highest value minus lowest value. For example, let's say time taken for year 12 students to complete a test is uniformly distributed between 30 and 60 minutes. So here B is 60, A is 30. So this is what the PDF looks like. Now this number here, the height of the PDF has to be 1 over 30 because the area under this distribution must be 1. If I integrate 1 over 30 between 30 and 60, I would get 1. So the PDF is just 1 over 30 for these values. So to get the CDF, what we do is we integrate the PDF from the lowest value X can take up to X. So the integral of 1 over 30 is just X over 30, and we're integrating between 30 and X. Now, if I substitute X for X, well, I'm just going to get X over 30 again. If I substitute X for 30, I just get 30 over 30. So the CDF here would be X minus 30 over 30. So that CDF is a function that allows us to calculate the probability X is up to and including a certain value. So for example, if I wanted to calculate the probability that a student took less than or equal to 40 minutes to complete, I can just substitute X for 40. 40 minus 30 is 10, so it would be 10 over 30 or 1 over 3. That's what the CDF is. But let's look more at a PDF now. So let's change the question on the previous slide a little bit. Let's say it still takes students between 30 and 60 minutes to complete, but this time the PDF isn't going to be uniform because we're going to have a clear mode. Most students take about 50 minutes. Now, when there's a clear mode, rather than use a uniform distribution, you use a triangular distribution. The PDF is actually made up of 2 lines, one line here and one line here. That's why it's called triangular, because its PDF is a triangle. So the area under this triangle must be 1 because this is a PDF. So that determines the value of H. See, the area of any triangle is base, so the base is 30. Base times height over 2. And that area here must be 1 because it's a PDF. So solving this equation, we just get h is 1 over 15. So from that, we can answer questions about probability. So let's say a student is selected at random and we want to find the probability they take between 45 and 55 minutes to complete this. So really what we're being asked to find is this area in here between 45 and 55. I know the area under the whole triangle is 1, but I want to find that area here. So what I'm going to do is divide it into 2 trapeziums. So 1 trapezium over here, 1 trapezium over here. Now, if I want to find the area of the trapeziums, I need to know this value here and this value here because they are the sides of the trapeziums. So what I need to do is find the equation of the black line and the equation of the red line. So I know that the black line goes through the point 30, 0, and 50, 1 over 15. So to calculate the equation, I must first find the gradient. So the gradient is y2 minus y1 over x2 minus x1. It's 1 over 15 divided by 20, which is 1 over 300. So to find the equation of the line, I take this equation y equals mx plus b. I'm going to substitute m for 1 over 300, x and y from a point, x30, y0. So solving this equation for b, I get b is negative 1 over 10. So the equation is y equals mx plus b. So now I'm going to go ahead and do something similar to find the equation of the red line. So the red line passes through this point 50, 1 over 15, and this point 60, 0. So once again, I calculate the gradient as y2 minus y1 over x2 minus x1. So I get negative 1 over 15 divided by 10, which is negative 1 over 150. I would expect the red line to have a negative gradient because it leans to the left. So I've just found the gradient. To find the equation of the line, I'm going to substitute m for negative 1 over 50, x and y from a point. I'm going to choose x60, y0. So if I solve this equation for b, I get b is positive 0.4 or 2/5. So the equation of the line is y equals mx plus b. So why did I find the equation of both lines? Well, that will allow me to find this value here and this value here. To find this value here, I just substitute 45 into this equation. So if I substitute 45 into this equation, I actually get that this height here is 0.05. So if I now substitute x equals 55 into this equation here, I get that this height here is 1 over 30. So now I'm going to calculate the height of both trapeziums. So this first trapezium here, I'll call that T1. So its area is going to be h over 2 times the sum of the 2 parallel sides. So 0.05 plus 1 over 15. And then trapezium 2, its height is also 5 times the sum of its 2 parallel sides. And all I need to do is add these together and I have my answer. So the total area highlighted here between 45 and 55 is your 7 over 24 plus 1 over 24, which gives me 13 over 24. That's my probability and I'm done. All right, let's now look at fixing a PDF. So sometimes you'll get a function like this and you'll be asked to fix it so it's a valid PDF. So let's look at what makes a valid PDF again. Well, we know, firstly, this function is always going to take positive values for x is greater than 1, because this will be positive. So it's not the first condition that's violated, it's actually the second condition. So if x can be greater than 1, that means x goes from 1 to infinity. So if I am to integrate from 1 to infinity this function here, it turns out I won't get 1. So this is x to the power of minus 5. So what you do to integrate that is you increase the power by 1 and divide by the new power, going from 1 to infinity. So just making this a little easier to work with, this would be minus 1 over 4x to the power of 4. Now, when you substitute in infinity, we're going to get that the function equals 0. See, minus 1 over 4 times infinity, you can read that as minus 1 divided by a really large number. If you take negative 1 and divide by a really large number, that becomes 0. When I substitute x equals 1 into this, I just get minus 1 over 4 times 1. and I get 1/4. So it becomes 0 plus 1/4, which is just 1/4. So this function here can't be a valid PDF for x is greater than 1 because the area under the curve is 1/4. It's not 1. But I can easily fix this. See, if I just multiply this by 4, that means that the final area will be multiplied by 4 and it will give 1. So I've now fixed it. Turns out 4 over x to the power of 5 for x is greater than 1 will be a valid PDF. So let's now use this to find the expected value, variance, and median. So these are the formula here for expected value, variance, and median. This is the PDF we fixed up on the previous slide. So to start with, we're going to find the expected value, also called mu. So to do that, you integrate over all possible values of x, and it's x times the PDF. So that's just the integral from 1 to infinity. See, x over x to the power of 5 is x to the power of minus 4. So when I'm integrating it, I'm just going to use the rule increase the power by 1 and divide by the new power. So just making this a little easier to work with, we'll write it as negative 4 over 3x cubed from 1 to infinity. So once again, when I substitute infinity, I get 0. Minus 4 divided by a really large number gives you something really close to 0. If I substitute x is 1, I get minus 4 over 3. So the expected value here is positive 4 over 3. Note the expected value must always be in the range of possible values for x. So if we got a number less than 1, we knew we'd done something wrong. So that's the expected value. I'm going to get rid of that now to find the variance. Please pause and copy down if you need. So to find the variance, which is sigma squared, it's kind of similar to the expected value, except you integrate over all possible values of x squared times the PDF. And then you have to remember to subtract mu squared. So remember mu, the expected value we just figured out was 4 over 3. You need to find the expected value to find the variance. This is the formula we went through last semester. It's e of x squared minus the expected value all squared. So let's now evaluate this integral here. So that, of course, becomes the integral 1 to infinity x squared divided by x to the power of 5 is x to the power of minus 3. So to do that integral, we're going to increase the power by 1 and divide by the new power. So making it easier to work with, I'm just going to write it as minus 2 over x squared. So once again, if I substitute in infinity, I get 0. Negative 2 divided by a really large number squared will give me something close to 0. Now when I substitute in x equals 1, I'm going to get minus 2 over 1. And then minus 4 over 3 squared is actually 16 over 9. This is just 2 minus 16 over 9, which gives us 2 over 9. The variance here is 2 over 9. Note that the variance must always be a positive number. So if I was asked to find the standard deviation, well, we just find the variance as we've just done and then square root it. So the standard deviation would just be the square root of 2 over 9. And that gives us 0.47. So that's all for the variance and standard deviation. I'll now calculate the median and get rid of this working out. Please pause and copy down if you need. So the median's a bit tricky, so I'll show you visually what we're finding. So our PDF is going to look something like this. So what we've found is that from x equals 1 all the way to infinity, this goes on forever and ever, we know that the area underneath the curve, this area here, is going to be equal to 1 because it's a PDF. So what we're trying to do when we find the median, we're trying to find there will be some value along here. We're trying to find the x value that divides the area in half. So 50% of the area is below it and 50% of the area is above it. We want to find that value k. So what we do is we integrate from a, the lowest value that x can take, in this case 1. So from 1 up to k of just the PDF. We don't times it by x or anything. So we want that to equal 0.5. This is actually an equation where we're solving for k. So this is 4x to the power of minus 5. So to integrate that, we increase the power by 1, leave the 4 alone, but divide by the new power. So that's between 1 and k, and that just simplifies to negative 1 over x to the power of 4. So we want this integral here to be 0.5. So if we substitute k for x, we're just going to get -1 on k to the power of 4. If we substitute x for 1, we're just going to get -1 on 1. And that needs to equal 0.5. So what we have is -1 on k to the power of 4 plus 1 equals 0.5. So we have -1 on k to the power of 4, subtracting 1 from both sides is -0.5 or -1/2. Now we can flip each fraction and take away the negatives. We get k to the power of 4 equals 2, or k is the 4th root of 2. So the 4th root of 2 is about 1.19. So that's the value along this x-axis. So 50% of the area is below and 50% of the area is above. All right, let's now look at laws of expectation and variance. So these are the laws for expectation and variance. Now on the previous slide, we found that the PDF of this function gives us an expected value of 4/3 and 2/9. How would we calculate the expected value of 3x minus 2? Well, expected values are easy. If we're going to multiply the random variable by 3 and then subtract 2, all we do to his expected value is times it by 3 and then subtract 2, and you get 2. See, this law here makes sense. It's very commonsensical. The expected value is just the mean. So think about like our class mean for a test. If I took 2 off everybody's score, the mean would decrease by 2. If I tripled everybody's score, then the mean would also triple. But for the variance, it's not actually the same. So look at the variance of 3x minus 2. So if I took 2 marks off everyone's score in a test, it actually wouldn't change the variance, because the variance is a measure of how spread out the scores are. Taking 2 from each score doesn't change how spread out they are. Now, it turns out if I triple everybody's score, I won't triple the variance, I'll multiply it by 3 squared, which is 9. So if the variance of x is 2/9, the variance of 3x minus 2, I need to take the variance and times it by 3 squared, but I ignore this -2 here. Adding or subtracting from each score does not change the variance. So it's just 2/9 times 3 squared, and here the variance would also be 2. All right, let's now have a look at normal distributions. So a normal distribution is a very important distribution. They always look like this or this. They have some things in common. They're always bell-shaped and symmetrical, so the mean and median are always the same. What that means is, for this red one here, it's a PDF, so the area underneath is 1, so half of the area is below the mean and half is above the mean. So whether it looks like this or looks like this, how fat or thin it is determined by mu, which is the mean, and sigma squared, which is the variance. Now, the PDF of a normal distribution is very complicated. It's this here. Notice that there's a sigma and a mu in there. We can't actually integrate that using functions. We can't do it by hand. So what we do, if we want to find probabilities using a normal distribution, we find how many standard deviations a score is from the mean. See, it doesn't matter whether the distribution's like this or like the blue one, whether it's really tall or really short, whether it's fat or thin. Normal distributions, regardless of their mean and standard deviation, they always follow this rule here. So there's 34.13% of scores between the mean and 1 standard deviation above the mean, and so on. It's usually called the 68, 95, 99.7 rule. In any normal distribution, 68, or more precisely 68.26% of scores are within 1 standard deviation from the mean. 95.44% of scores are within 2 standard deviations, and 99.74% of scores are within 3 standard deviations. So if you have a score and you want to find how many standard deviations above the mean it is, you use this formula here. You give it a z-score. The score minus the mean over the standard deviation tells you how many standard deviations the score is above or below the mean. So if a z-score is less than 0, if it's negative, it's below the mean, and a positive z-score means above the mean. So if you take a score x from a normal distribution and you convert it to a z-score, what you're doing is you're converting the normal distribution with some mean and some variance into what's called the z-distribution or the standard normal distribution. See, Z is a special normal distribution that has mean 0 and variance 1. So that's what all these red numbers are here. For a Z distribution, standard normal distribution, it would have 95.44% of scores, for example, would be between -2 and 2. All right, let's look at how we'd actually use this to solve probability problems. So let's say, for example, heights are normally distributed with mean 170 and standard deviation 10. Select a student at random. What's the probability they're between 160 and 180 centimeters tall? So here I'm going to let X be the height of a randomly selected student. It is normally distributed with mean 170, and we write here not 10 but 100. We always write the variance here. So the variance is 100, which is 10 squared. The standard deviation is 10. So to find the probability of being between 160 and 180 centimeters tall, I'm going to convert both of these scores into a z-score. So to do that, I take score minus mean divided by standard deviation. I take score minus mean divided by standard deviation. So what have I actually found? I've found that 160, anyone who's 160 centimeters tall is one standard deviation below the mean. Anyone who's 180 centimeters tall is one standard deviation above the mean. So the probability in a normal distribution of being between one standard deviation below and one standard deviation above the mean is 68.26%. We saw that on the previous slide. So what about this one, between 166 and 178 centimeters tall? Well, if I convert them to z-scores, 166 score minus mean over standard deviation, I get minus 0.4. For 178, if I subtract the mean and divide by the standard deviation, I get 0.8. So if you're 166 centimeters tall, you're 0.4 standard deviations below the mean. If you're 178 centimeters tall at this school, you're 0.8 standard deviations above the mean. So the problem is the diagram we looked at in the previous slide only talked about whole number z-scores. We can't possibly remember the probability of having a z-score that's any value, including non-whole numbers. That's infinitely many. So when the z-scores are not whole numbers, if we want to calculate probabilities, we need to use our graphics calculator. So what we do is we go to the distribution menu and use the normal CDF function, and we just input the values. We input the lower value we want, the upper value we want, and then we put the mean and the standard deviation. So putting this on a calculator, we get about 0.44. So 44% of scores in a normal distribution have a z-score between minus 0.4 and 0.8, and we're done. All right, let's look at a more challenging question now. So let's try this one. Time taken to run 100 meters, normally distributed. 15.8% of students take longer than 14.3 seconds. 2.28% of students can run in under 11 seconds. We're going to find the mean and variance of the time taken. What we really need to do is we need to figure out for this score, 14.3, how many standard deviations above or below the mean, and similarly for the score of 11. So we learned on the previous slide that at one standard deviation above the mean, there are 15.87% of scores above it, and the rest, the other 84.13% of scores below it. So what that means is this score of 14.3 represents one standard deviation above the mean, so it's mu plus sigma. We also saw that for a normal distribution, there are 2.28% of scores lower than a score which is minus 2 standard deviations from the mean, or 2 standard deviations below the mean. And that, of course, means the other 97.72% are above. What I've just found is this score of 11 is mu minus 2 sigma, 2 standard deviations below the mean. So we're going to solve these simultaneously. That's our go-to method when we're finding two unknown quantities at once. So we're going to subtract the equations to eliminate mu. So 14.3 minus 11 gives 3.3. Mu minus mu is 0. Sigma minus negative 2 sigma is positive 3 sigma. So that means the standard deviation is 1.1, and that means the mean must be 13.2. How easy is that? All right, let's now have a look at quantiles. So quantiles are when you're sort of going the opposite direction. What we found in previous questions is we knew the value. We wanted to find the probability we were above or below a certain value. Now, in these questions where we're using quantiles, we already know the probability and we want to find what is the number such that being less than or greater than that number equals a given probability that we already know. So let's say X follows a normal distribution with mean 32 and variance 9. So that means that the standard deviation is the square root of 9, which is 3. So this is what I'm doing. I have some normal distribution here, and the mean I know is 32. I want to find what is the value here, K, such that 20% of scores are below it and 80% of scores are above it. So it's obviously going to be a number less than 32. Now to do this, we go to that distribution menu and we use inverse normal. You always use that for quantiles. So in the inverse normal function, we put the area, which is the same as the probability, and then just put the mean and the standard deviation. So putting that on our calculator, we get about 29.48. So what we've actually found is if the mean's 32, standard deviation's 3, 20% of scores will be less than 29.48. So what about this one here? This time we want to find K so that the probability of being above K is 0.2. So it's sort of like the opposite. We still have our normal distribution here and the mean is 32, but this time we want to find K, so it'll be greater than 32. We want to find K so that 20% of scores are above it. Now this inverse normal can only solve problems like this, where the probability of being less than that value is known. So if the probability of being above K is 0.2, that means the probability in this question of being less than K is 0.8. So we're going to have to put 0.8 into this function inverse normal because it only calculates when you want to be less than a certain value. So here we'd put inverse normal 0.8, 32, and 3. And then we get the number 34.52. So if you have a normal distribution, mean 32, standard deviation 3, then 20% of scores are above this number, 34.52. So what about this one here that's a bit tricky? We're going to need to draw a diagram. So here we want to find a value K such that 10% of scores are within K units of the mean. So the problem is our inverse normal function only calculates when you know the probability of being less than a certain value. Now, because of the symmetry of a normal distribution, 5% of scores, 0.05, will be the probability of being in just this part here. We also know that the probability of being less than the mean, this whole area here, would be 0.5. That works for any normal distribution. So what we have is that the area of being less than 32 minus K, this area here, must be 0.45. So now we can transform this into an equation. Here we have the probability that X is less than 32 minus K is equal to 0.45. So we can use our inverse normal function. So putting that on our calculator, we get about 31.62. Now, that's not the value for K. That's the value here. 45% of scores are less than 31.62. So we've got 32 minus K equals 31.62. So K is about 0.38 and we're done. All right, let's do one more example where we're finding the mean of a normal distribution. So the time taken to complete a maths test is normally distributed, and we know that the variance is 36, which of course means the standard deviation is 6, square root of 36. So we're told 74.75% of students take longer than 32 minutes to complete, and we're going to calculate the mean time taken to complete the test. So whenever you're doing a problem involving normal distributions and you have to find the mean or variance, always use z-scores. What do I mean by that? Well, I know this score of 32, 74.75% of scores are above it. What I really want to find out is 32, how many standard deviations is this from the mean? So I want to use the Z distribution. In particular, I want to find a value Z such that 74.75% of scores are above it. So I need to use the inverse normal function on the graphics calculator. But remember, the inverse normal function can only calculate when you know the probability of being less than that value. So I really want to find the value Z such that being less than that is 1 minus 0.7475, which is 0.2525. So I put in my calculator inverse normal 0.252501 because the mean of the Z distribution is 0 and the variance and standard deviation are both 1. So putting that on my calculator, I get minus 0.6666. What does that actually mean? It means in any normal distribution, 74.75% of scores are above 0.6666 standard deviations below the mean. So what I've actually found is that this score of 32 is 0.6666 standard deviations below the mean. So let's use the z-score formula. That means the score minus the mean over the standard deviation is equal to this number minus 0.6666. So all I do is solve this equation. I multiply by 6. I get that 32 minus mu approximately equals 4. So mu is 32 subtract negative 4, which is 36. So that means the mean time taken to complete this test is going to be 36. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.